Good morning. Welcome to the solution video to problem C of the 2021 Facebook Hacker Cup qualification round. In this problem, gold mine, we have a mine with a bunch of caves and then a bunch of very sketchy edges between these caves, where the edges are so sketchy that we don't want to pass through them any more than once if we have to. So we have this cave, which is in the form of a tree, and we have different amounts of gold in each cave in this cave system. And we want to get as much gold as possible, obviously, but we want to do it in such a way that we only travel through each edge at most once. Now that's a bit of a problem because if we go down an edge, we need some way of getting back up. So to help solve this, we have one teleportation device, which lets us teleport from one node to any other node. But we can only use it in problem C1 at most once, and in problem C2 at most k times. One thing that's pretty helpful for this problem is that the graph is rather small. We only have 50 nodes, and k is at most 50. So it isn't too difficult on that front, but we still do have to come up with a good way of finding the most gold we can obtain under these kind of complicated restrictions. In the first problem, we have something that looks like this. And one thing to notice is that our optimal path that we end up taking is going to end up starting at the root, going down through several nodes. And then we're going to need to teleport because we can't go back up. So we're going to teleport maybe to some other node, maybe like this, over here. And then we're going to travel all the way back up to the root. It turns out that this is the optimal solution for this problem. And the way we can find what the best solution is we can just say, for each node, what's the best path going all the way down? Now this works because if you look at this path, we can consider both of these edges, although they're technically paths going down and then going up, we can look at both of them as going down, because it doesn't really matter which direction these edges are traveling, all that matters is which nodes they hit. So these two paths are going to go down, and we want the best two paths to do this, where the only node they share is the root node. In other words, the only edge they share is the empty set, right? They don't share any edges at all, because we can't use any edge more than once. So we can do this by just having a recursive function that says for each node, what is the score of the best path down from this node to some leaf. We can evaluate this for each node, and then for the root node, we can say for two different children, what is the best sum you can get. So for the root node, you'll want to use your best child and then your second best child. In this example, the best child from the root would be this path. And although the second best path isn't something we can use, because the second best path would go to this leaf actually, we can't use that, but the second best child from the root would go down to this leaf, and then that ends up being exactly the solution we're going for. So for problem C1, all we really need is a recursive descent through this tree, and that should be good enough. C2 is a bit more challenging though. So before I discuss the solution, I'm going to talk about one small simplification that I think makes it easier to understand. And that simplification is, let's look at the path that we end up taking. It might look something like this. So we'll take some path down here. Then we'll end up teleporting. Maybe in this case, we teleport over to this position. Perhaps we take some path like this. Then we teleport maybe over here. We take some path. Finally, we teleport down here. We take another path. And then we teleport somewhere else, and then we take a path to the root. So in this case, although it's a bit messy, we have done a total of 4 teleportations, so we'll say k is equal to 4. And then in this case, we have 5 contiguous segments of the tree. So we have something from the root down here, we have another continuous segment in the tree, another one here, and then finally one back to the root. So we have 5 continuous segments. But we have these constraints on the first and last segment, which is the first one has to start at the root, and the last one has to end at the root. We can combine these into one segment, and that makes everything a lot easier. So we know these are adjacent, so let's instead pick something like this. And now we can easily glue these segments together in any order. We know there's at least one segment that contains the root, but other than that, we don't have any requirements on these segments at all, besides them being disjoint. So if we have some edge disjoint segments, then we can take any set of edge disjoint segments where at least one contains the root, and we can construct our answer from it if we need to. So this is a little bit easier of a problem, I think. This problem is just find k sets of segments on the tree where none of the segments overlap, and then the sum of the segments is as big as possible. They can overlap on nodes, they just can't on edges. So in this example, they didn't overlap on any nodes, but they could have. That would be okay. So how do you do this? Well, this is certainly a little bit of a messy problem to solve, but we can do it if we need to. And I think there are several ways of approaching the problem, but the approach that I used is I did a DP. So we did a DP at some node, and really we're doing it along some edge of the tree. So we're saying for some node, and then also which node's child you're at, right? Which version of that node's children you're considering. We're gonna do this DP, so the node, and then also which child. And then the sum of all of these values is just going to be order n, because there are only n-1 edges in the tree. So in total, this will be order n. And then we also need to store in our DP state how many paths we're going to consider within this subtree. So if you imagine this, we've got, let's do this in red here. If you imagine we're looking at this subtree here, the subtree rooted at this node. We want to say how many paths are entirely within the subtree, and this is like the number of paths. But we also have one other thing that's important to keep track of in this node, which is whether we have a path that we can continue from this node. So whether this is like continuable. For free without starting a new path. Now we can always subtract one path and then make this like continuable. And because of that, I think it's a little bit easier to implement if instead of storing whether this is a Boolean, which is what we do in the model solution, we can store how many endpoints are available, right? So we can just store the number of endpoints. And then when you create a new edge, you'll create two endpoints. They're both the same node, and then you can extend both of them along different paths. Or you can create or you can have one endpoint, which is passed in from your parent, possibly. And then you can push that endpoint down to one of your children. And then if you want, you can create two new endpoints at yourself, because you could have some node like this. You might have some path coming from your parent down to one child, and then you might create a new edge here that goes like to a different child. They have to be disjoint, so it'd be like to a different child here, and then to some third child like that. So this would be this root of this, like the place that we count this additional creation of some path is at the lowest common ancestor of all of the nodes on the path. So that's an easy way of counting it. And finally, we need one more part of this DP value, which to me, I called it whether we are going to whether we're forced to count this node. So this is useful in two parts of the DP for me, for my implementation. The first part is the root node of the tree we have to take. That needs to be part of at least one edge. So we can set that to 1 because we know we have to take it. It's also helpful for me because if we have some node, it's possible this node has a lot of children. Now we're allowed to create an edge here, and we can create some edge here, and then we can push the two edges down. And in this case, we get the benefit of ourself here because this is the first time this node is used. So we get the additional value of this node because we get all of the gold in it because we know it's part of a path. But we don't want to, we also are allowed to create a second edge like this, but we don't want to double count the value at this node because we'll already receive the gold at this cave. We don't want to count it twice. So we can use this bit here to say whether or not we have counted ourselves as being part of some path already. Initially, if we're not forced, or if we are forced to take it, that means that this node's going to end up being taken, and also we haven't yet accounted for the fact that it's going to be taken. And then once this bit gets set to 0 in our DP, now we know, okay, well, this bit has been taken, so either we're never going to end up taking this at all, or we've already taken it in one of our previous children that we were processing. So what is the total runtime of this? Obviously, it's not going to TLE because, well, A, the time limit is rather generous because you've got several minutes to run your code, but B, the graph is very small, so it's not going to be an issue. But this part is bounded by n. This is order n. The number of paths that we have, this is order k. This part is order k. The number of endpoints is a constant, so this is just 3. And then the number of times that whether or not we're forced to count this is also a constant, it's just 2. So our total state is n times k times a constant. And the runtime, I didn't talk about this directly in the analysis of the DP, but we have the number of paths that are within this subtree. When we're considering our next child, we have to brute force how many paths are going to be within that child subtree. And the rest of it will be within the rest of our kids or ourselves. We might start one at ourselves. But other than the path at ourselves that we start and the path of the rest of our kids, the rest of the paths go to this child. So we need to decide how many of those paths we're going to give, and that's an extra factor of k for the transition. So the final runtime looks like this. You can also make this the min of k and n, I believe, if you do a little bit of work in your DP. So it's about order 50 cubed is the runtime. Plus you have a little bit of overhead from the fact that you've got some constants here, but overall it's nowhere near a TLE, so you should be absolutely fine on the runtime, as long as you remember to memorize. So hopefully you enjoyed the problem. It was a bit more challenging than A or B, and I thought it's a good learning experience, especially if you're new to tree DPs.